All right, so our next speaker is Courtney Thatcher from the University of Puget Sound, talking about classifying ZP cross ZP actions on products of spheres. Take it away, Courtney.
Okay, thank you. Hopefully everybody can see the slides okay. So just briefly what the contents of the talk. And so I want to start with some history because I think it's a really interesting, rich problem, and it gives a lot of context for why we're doing what we're doing. And so I'll talk about the topological spherical spaceform problem. So I'll give a little bit of history, what we can say about what groups can act on a sphere, and then talk about how they act. And so that's the story of Limbspaces. And then I will shift to a natural next question: how can groups act freely on products of spheres? So we can talk a little bit about what can actually act, and then I'll focus on how things act. So how do some of the simplest groups act? And so I'll say a little bit about Z mod P, one of the simplest possible things that could act on the product of two odd-dimensional spheres. And then some of the more recent work. So I'll say a bit more about this. This is joint work with Jim Fowler at Ohio State. And so that will be some of the more recent stuff. So I will end with talking about where some of that stands. And then I have a list of references if you are interested. Okay, so what is a spaceform? So this goes all the way back to 1890s. And so a spaceform is a closed Riemannian manifold with constant sectional curvature. It turns out the spaceforms are quotients of the standard models, so Euclidean space, spheres, and hyperbolic space, by free and properly discontinuous actions of discrete groups of isometries. And so Hopf started working on three-dimensional spherical spaceforms in the 20s. And so the topological spherical spaceform problem is a generalization of this. So you can ask what groups can act freely on the sphere, and how do they act? How do you classify the actions that are possible? Okay, so we're going to talk about these two questions, and then when we shift to products of spheres, we're going to ask similar questions. So these are our two big questions: what groups can act, and how can you classify the actions? Okay, so if you're looking at an even dimensional sphere, the only thing that can act is Z mod 2. This is by the Lefschetz fixed point theorem. And so these end up just being real projective space. So I'm not going to say much about this. That's most of the story. It's well studied, lots of information about projective space, but we're not going to talk about that. So instead, I'm going to focus on odd dimensional spheres, S2 and -1. And so there are two conditions, and it turns out they are sufficient for a finite group to act freely on an odd dimensional sphere. So there's this one from the 40s from Smith that says every subgroup of order p squared has to be cyclic. And so this is called a p squared condition. It has to be true for all primes. It ends up being equivalent to finite groups of periodic cohomology. And in particular, it tells us things like ZP cross ZP cannot act. So we can already rule out things like that. And so that'll be important when we go to shift to products of spheres. There's the second condition from Milner in the 50s that every subgroup of order 2p must be cyclic. And so this gives us things like dihedral subgroups cannot act. So we can't have groups that contain dihedral subgroups. And that will also be important when we shift to products of spheres. Okay, I don't have a lot of pictures, so I thought I would write on my slides. So hopefully this is legible. Okay, so it turns out those are sufficient. Okay, so let's start. So those are what can act, and then you can ask, well, how can they be classified? And so this turns into the classification of Limbspaces and fake Limbspaces. So I want to talk a little bit about Limbspaces and fake Limbspaces. So what on earth is a Limbspace? So a Limbspace is the quotient of a free Z mod n. So I'm not just taking primes at this point. So n can be any positive integer. A free Z mod n action on an odd dimensional sphere, which we think of as living in complex space. And so the action is given by these rotations. And so the way to think about this is we can think of the odd dimensional sphere as being the join of n copies, join of S1. And so for each of these spheres, we get a rotation number. And so suppose, say, n is 3. So we can think about, splitting this up into thirds. And so if your rotation number, say, is Li is 1, then you're going to rotate by 2 pi Li over n. So we're going to rotate by 2 pi thirds in this example. Okay, and so you get a rotation number for each of the spheres. And then the quotient is what we call a lens space. And so we often write it as L, where you indicate the n in your group and then all the rotation numbers that are associated with it. Okay, so this is a lens space. This is a classical lens space. They were originally defined just for S3. They were 3-dimensional, and then it was extended to higher odd dimensions. Okay, so those are our lens spaces. It turns out that lens spaces have a natural CW structure with exactly one cell in each dimension. And they have the same homotopy groups and the same homology groups when you fix your group and dimension. But it turns out they do not all have the same homotopy type. And these were the first spaces that actually were used to show this. So they were really important in algebraic topology. It turns out the first k-invariant of a lens space is the product of its rotation numbers, and I should say times a certain cohomology class. So we could write the k-invariant of a lens space is we take the product of all these rotation numbers, and then there's a cohomology class they're multiplied by. And then it lives here. There exists a homotopy equivalence between two lens spaces that preserves orientation and preferred generator if and only if the product of the lens spaces is the same mod n. So you just multiply all your rotation numbers, and if they're the same mod n, then you know that there is an orientation preserving homotopy equivalence. If you don't care about preserving orientation and you're willing to change generators, then you just need to add in this plus or minus k to the d term. So k is some element of z mod n, and d is related to the order. It's actually, yeah, I think this is actually an n. So it's related to the degree of your sphere. So my apologies. Okay, so we know that. Oh, and let me actually go back for a second. And so playing around with these numbers, you can immediately show things like, if we're looking at z mod 5, the lens space you obtain from rotation numbers 1, 1, and the lens space you obtain from rotation numbers 1, 2, cannot be equivalent plus or minus anything in z mod 5 squared. And so you get immediately that these are not homotopy equivalent. And so these are some of the first examples of things that are not homotopy equivalent. Okay, and then for simple homotopy equivalence, the rotation numbers have to be exactly the same up to permutation and multiplication by one element of z mod n. Okay, and so from this, you can get things like, if we're looking at, say, z mod 7, the 3-dimensional lens space with rotation numbers 1, 1 and 1, 2 do end up being homotopy equivalent in this case, but they're not simple homotopy equivalent. It also turns out that this is the same story for homeomorphism. So the same condition holds. And this is due to Brody in 1960. Okay, so where do you go from here? So we have these classical lens spaces. We know when they're the same, and we know how to distinguish them. What if we want to look at actions that are not necessarily this rotation action? So we can look at what's known as fake lens spaces. And so this is the orbit space of any free z mod n action on an odd dimensional sphere. It turns out every fake lens space is homotopy equivalent to one of the classical ones with the rotation numbers, but they're not necessarily homeomorphic in the same way. And so if n is odd, then fake lens spaces are determined up to homeomorphism by the Reidemeister torsion and the row invariant. So the Reidemeister torsion is directly related to like Whitehead torsion and simple homotopia equivalence story. And the row invariant is an odd dimensional invariant that's related to things like equivariant signature. So you see it in the surgery theory story. The results can be extended to even n as well. And you need some additional invariants for that. And those are known as the splitting invariants. So we have this collection of invariants for fake Limbspaces. Okay, so where do we go from here? So we have this very interesting story about actions on odd-dimensional spheres. So you might ask, what about products of spheres? So there's a lot of different things you could say about products of spheres. I'm going to focus on the case of the product of two odd-dimensional spheres of the same dimension. So S2 and minus 1 cross S2 and minus 1. And then you can ask what you do, once you know what can act, how can you classify these group actions? And so that will be, we'll talk about a couple of the simplest actions. Okay, so what groups can act? What do we know at this point? It's not, we don't have a complete answer, actually. Okay, so we know that for a group to act freely on S2n minus 1 cross S2n minus 1, it can have at most rank 2. And so that means we can't have things like ZP cross ZP cross ZP. And so this is really similar to the p squared condition. So we can't have things like this. So we have a similar condition to the p squared condition for the single sphere case. But what happens within the rank 2 groups? Some of them can't act. So for example, A4, the alternating group of degree 4 cannot act on S2n minus 1 across S2n minus 1, and that actually rules out every rank 2 simple group. There are also some funny things like this. So there are products of finite groups that act freely on a product of spheres, but the individual factors themselves do not act freely on a single sphere. And so, for example, if DQ is the dihedral group of order 2Q, you can show that DQ cross DQ can act on, say, S7 cross S7. But we know from the 2P conditions that DQ can't act on S7. So we have some strange things going on. And we know that there isn't an equivalent condition like the 2P condition in this case. So something else is going on. The correct conditions are not quite known. You can do, for example, free actions by subgroups of non-abelian extensions of S1 by ZP cross ZP. So those examples have been constructed, but on the other hand, QDP cannot act freely. And so there's this question of where can you draw the line? What can act and what cannot act? So lots going on there. Okay, so now I'm going to shift to some of the simplest groups and how they act. So how can we actually classify those actions? And does that tell us anything about other groups that may or may not be able to act? Okay, so let's look at Z mod P. So this is one of the simplest groups we could ask to act on S2n minus 1 cross S2n minus 1. So how could you classify these? A really simple example of one of these is you could just have the Z mod P act on one of the spheres and not at all on the other. That is a free action. And that would result in a Limbspace cross a sphere. So we know some of them, but is that the whole story? So we could have, say, L, P. So what are the others? So what can we say? Well, it turns out, so in the Limbspace case, if you think about writing out the Postnikov tower, there is only one k-invariant, and it is that product of rotation numbers. And then the Postnikov tower becomes formal after that point, because the k-invariant corresponds to the highest dimension. When you're looking at products of spheres, there is that sort of first k-invariant that happens at 2n minus 1, just like the Limbspace case. But there's a whole bunch of other ones that are in there as well before the process becomes formal. It turns out you actually only need that first one, just like the Limbspace case, to determine if two are homotopy equivalent. So that's actually kind of neat. And then because we're now in an even dimensional quotient, an even dimensional manifold, we get simple homotopy equivalence for free. So the evenness there are no obstructions to having a simple homotopia equivalence. Okay, what else can we say? We knew that fake Limbspaces were determined by the row invariant and Reidemeister torsion, but for the exact same dimension reasons, we're in this even dimensional case, and the row invariant vanishes, and so does the Reidemeister torsion, the simple homotopy equivalent requirement, and we need something else to actually distinguish them. But because the row invariant vanishes, you can actually compute things like the simple structure set, and it turns out it's just p torsion. And in particular, you can actually use the Pontrjagin classes to distinguish these spaces. I do want to say, since the p torsion is only in degrees of 4 between 0 and the middle dimension, that 2n minus 1, you get things like, and I'll write it here, that if we're looking at S3 cross S3 mod a Z mod P action, then the simple structure set is 0. And so that immediately tells you that any two of these that are homotopy equivalent are homeomorphic. You have to pick up some things like that. And in particular, they could also be PL homeomorphic. So this is for category being PL and top. Okay. You can construct linear examples. And what I mean by linear in this case is that Z mod P acts on each sphere separately. And so you can use these rotation numbers in a similar way to Limbspaces and construct these linear examples. And for a linear quotient, you can actually write out the Pontrjagin class explicitly. And it turns out that these classes end up being p-localized homeomorphism invariants for a given dimension. So you can use these to distinguish linear actions. Okay. So that's the sort of Z mod P story. What about a slightly more interesting action? So ZP cross CP actions on S2n minus 1 cross S2n minus 1. You could just have the first Z mod P act on the first sphere and the second Z mod P act on the second sphere. And so we get things like products of Limbspaces are examples of these types of actions. But are there more free G actions? Are there other possibilities? Does it just have to be a Limbspace cross a Limbspace? And no, it doesn't have to be. Okay. And once you have these actions, when are quotients homotopy equivalent? When are they homeomorphic? We can go through the sort of same story. Okay, it turns out we still only need the first k-invariant again. It works out very similarly in this case as well. The k-invariant is different. The way you calculate it is different. But you still only need that first one. The higher ones don't end up contributing anything. Also, because we're still in this even dimensional case, two that are homotopy equivalent are also simple homotopy equivalents. So we get that for free because we're even dimensional. What else can we say? So there's some natural questions you might ask about this. So how many homotopy classes of quotients are there? Can we actually count them in some way? And the answer is sort of. It's a little complicated, but there are some cases. And how do you compute the k-invariant, or are there cases where you can compute the k-invariant? Okay, so since everybody loves seeing spectral sequences in talks, I want to say a little bit about the spectral sequence for this. You can consider the Serre spectral sequence for the Borel vibration. So we can look at S2n minus 1 cross S2n minus 1, mapping into our quotient spaces, mapping into BG. So G again is our ZP cross CP. And without getting into too many details, our spectral sequence, we're going to have the cohomology of ZP cross CP across the horizontal axis, and we'll have the cohomology of S2n minus 1 cross S2n minus 1 going up. And so S2n minus 1 cross S2n minus 1, let's say it has cohomology in the 0th group. It has cohomology in 2n minus 1, and it has two generators for that. So I'm going to call them alpha and gamma. And then you end up with an alpha gamma up in 4n minus 2. ZP cross CP is interesting. It has a 2 generators in degree 2, and it has a generator in degree 3, which I'm going to call C. And then they combine in ways like this. So in 4, we have an A squared, an AB, a B squared. In 5, you multiply C by each of those, and it sort of keeps going. So let me just put in degree 2n. The generators would be an minus 1b, all the way to bn. So we get those generators. And everything else is zeros in this. So if you're thinking about the differentials, the first non-trivial differential is here, it's d2n, and it's going to take alpha to some linear combination of this an minus 1b, or yeah, up to bn. So that's what this says. There's some coefficients on that, and the same thing for gamma. And so this particular differential right here is called the transgression, and ends up being really important. And so we have these coefficients. So what can we say about this? Well, there's some restrictions on these coefficients. In particular, the coefficients, so these are the coefficients for the an term, cannot both be 0 for both of them. And similarly, these are the coefficients for bn. They cannot also both be 0. This is for dimension reasons. And so what do these restrictions actually give us? Well, it turns out the transgression actually encodes the k-invariant. It directly tells us something about it. You can use it to compute the k-invariant. And it can be used in certain cases to count homotopy classes of quotients. You can use it to compute the k-invariant. And you can also use it to some extent to show a group with ZP cross CP as a normal subgroup cannot act freely on S2n minus 1 cross S2n minus 1. So it can be used in that way as well. So it should give us some information about groups that can act. As a really simple case, we could look at S3 cross S3, and our transgression becomes this. It's really nice. I need to stop, so I'll stop in just a sec. You can think of them as binary quadratic forms, and this actually lets you count homotopy classes. And so if p greater than 3 is a prime, if p is 1 mod 4, there are exactly 4 homotopy classes. And if it's 3 mod 4, then they're exactly 2. And so you can actually use this to help count things. There's a lot here. This is defining a linear action. It's really roughly, I know there's a lot to process there, but it's basically thinking about ZP cross CP doing rotations on the first sphere and the second sphere. So you end up with these 4 sets of rotation numbers. It turns out once you define this linear action, you can do things like define the k-invariant and define the Pontrjagin classes. And so you can go through some similar calculations, trying to figure out the homeomorphism, distinguishing homeomorphism classes. You can also compute the structure set in a very similar way to what we did in the ZMod P case. But I think given time, this is a good stopping place. And so I have a bunch of references because there is a lot of work on this. So you can, I'll stop with this.
Okay, let's thank Courtney. So I have a question that's maybe too obvious, but I think everything you talked about today was the product of 2 spheres. Do you know anything about the product of more spheres where the difference between homotopy equivalent and simple homotopy equivalent might come back in?
Yeah, so if you're just looking at ZMod P actions, which are really simple, it turns out, I believe all the linear ones do end up being simple homotopy equivalent, but I'd have to go back and look at why that was the case. But they're not all linear actions. And so you can end up with some that are homotopy equivalent, but not simple homotopy equivalent. But they're harder to construct, or I should say I don't have constructions for them.
Right. Other questions?
Yeah, I have a question. So, you know, a lot of your theorems rule out certain sorts of actions. And I'm wondering, do those proofs carry over if you replace your spheres by arbitrary homology spheres, or might you be able to realize some of these forbidden actions in those cases?
That's a good question that I don't have a great answer to. Some of it definitely works for homology spheres. but I haven't looked into it as much. So I don't have a great answer at this point, but that's a great question.
Can I ask a question too?
Yes, please.
You had the assumption that P is bigger than N. How necessary this assumption is? Do you know these theorems hold for smaller P?
Right. I don't. I think they do hold for some of them, but there are some additional things that can happen in those cases. So this makes some of the calculations work out really nicely. And that is definitely something that I've been meaning to go back and look more into. So I don't.
Thank you. Thanks.
Sure.
Any other questions? All right, well, let's thank Courtney one more time. And I'll stop the recording.